On this video, we're going to be talking about hypothesis testing using a single sample, specifically large sample hypothesis tests for a population proportion. The fundamental idea behind hypothesis testing is that we reject the null hypothesis if the observed sample is very unlikely to occur if the null hypothesis is true. Now recall the general properties for sampling distributions of p hat. Our mu of p hat equals p. The standard deviation of p hat equals the square root of p times 1 minus p, all divided by n, as long as the sample size is less than 10% of the population. And third, when n is large, the sampling distribution of p hat is approximately normal. These three properties imply that the standardized variable z, which equals p hat minus p divided by the square root of p times 1 minus p divided by n, has an approximately standard normal distribution when n is large. Let's look at an example. In June of 2006, an Associated Press survey was conducted to investigate how people use the nutritional information provided on food packages. Interviews were conducted with 1,003 randomly selected adult Americans, and each participant was asked a series of questions, including the following two. When purchasing packaged food, how often do you check the nutritional labeling on the package? And how often do you purchase food that is bad for you, even after you've checked the nutritional labels? It was reported that 582 responded frequently to the question about checking labels, and 441 responded very often or somewhat often to the question about purchasing bad foods even after checking the labels. Based on these data, it is reasonable to conclude that a majority of adult Americans frequently check nutritional labels when purchasing packaged food. So we'll take a look at our null hypothesis, which is p equals 0.5, and our alternative hypothesis, where p is greater than 0.5. Now p is going to equal the true proportion of adult Americans who frequently check nutritional labels. We use p is greater than 0.5 to test for a majority of adult Americans who frequently check nutritional labels. Now for this sample, our p hat is going to equal 0.58. This observed sample proportion is greater than 0.5. Is it plausible a sample proportion of p equals 0.58 occurred as a result of chance variation? Or is it unusual to observe a sample proportion this large when p equals 0.5? So we're going to create a test statistic using z equals p hat minus p divided by the square root of p times 1 minus p divided by n. A test statistic indicates how many standard deviations the sample statistic p hat is from the population characteristic, in this case p. Here we find our statistic, our z, as 5.08. Next, we find the p-value for this test statistic. Now, notice that this is a capital P value. The capital P value, or the calculated probability, is the probability of finding the observed, or more extreme, results when the null hypothesis, or H sub O, of a study question is true. The definition of extreme depends on how the hypothesis is being tested. Capital P is also described in terms of rejecting the null hypothesis when it is actually true. However, it is not a direct probability of this state. In the standard normal curve, seeing a value of 5.08 or larger is unlikely. Its probability is approximately 0. So here we'll see that our capital P value is approximately 0. Now, since the capital P value is so small, we reject the null hypothesis. There's convincing evidence to suggest that the majority of adult Americans frequently check the nutrition labels on packaged foods. So let's talk about computing p-values. The calculation of the capital P value, or the p-value, depends on the form of the inequality in the alternative hypothesis. So if our alternative hypothesis is that p is greater than the hypothesized value, then here we have our z-curve and our calculated z, and the p-value area is in the upper tail. Now, if our alternative hypothesis is that p is less than the hypothesized value, Then in our z-curve with our calculated z, our p-value area is in the lower tail. And when our alternative hypothesis is that p does not equal the hypothesized value, in this particular z-curve instance, we're going to see that the p-value is the sum of the area in the two tails. So here we'll be calculating our z and our negative z. So how do you use p-values to make a decision? Well, to decide whether or not to reject the null hypothesis, we compare the p-value to the significance level alpha. If the p-value is greater than alpha, then we fail to reject the null hypothesis. And if the p-value is less than or equal to alpha, we reject the null hypothesis. So let's look at the summary of our large sample z-test for p. So our null hypothesis is that p equals the hypothesized value. Our test statistic is that z equals p hat minus p divided by the square root of p times 1 minus p divided by n. The alternative hypothesis and our p-values, we have that if p is greater than the hypothesized value, then our p-value will be the area to the right of the calculated z. If our p is less than the hypothesized value, then our p-value will be the area to the left of the calculated z. And if our alternative hypothesis is that p does not equal the hypothesized value, then our p-value will be 2 times the area to the right of z of our positive z, or 2 times the area to the left of z of a negative z. So assumptions. We can assume that p hat is a sample proportion from a random sample. The sample size n is large, meaning n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And 3, if sampling is without replacement, the sample size is no more than 10% of the population size. Let's look at an example. So here, a report states that nationwide 61% of high school graduates go on to attend a 2-year or 4-year college the year after graduation. Suppose a random sample of 1,500 high school graduates in 2009 from a particular state estimated the proportion of high school graduates that attend college the year after graduation to be 58%. Can we reasonably conclude that the proportion of this state's high school graduates in 2009 who attended college the year after graduation is different from the national figure? Here we're going to use alpha equals 0.01. So first we'll state the hypothesis. So we have our null hypothesis is that p equals 0.61, and our alternative hypothesis is that p does not equal 0.61. P is the proportion of all 2009 high school graduates in this state who attend college the year after graduation. So assumptions. So we have to make sure everything's been met. We were given a random sample of 1,500 high school students, so that checks that box. Because 1,500 times 0.61 is greater than 10, and 1,500 times 0.39 is greater than 10, our sample size is large enough. So now we just need to check our third condition. Our population size is much larger than our sample size. So we're now good to continue on. So here we'll take our test statistic and we'll plug in our values, which is going to give us a z-value of -2.38. This is going to be the area to the left that we're going to be looking at. And if we look at the area to the left of -2.38, we're going to find that that's approximately 0.0087. Because our alternative hypothesis is that p does not equal 0.61, we're going to multiply 0.0087 by 2, giving us a p-value of 0.0174. Remember that we're using alpha as 0.01. So since our p-value is greater than alpha, we're going to fail to reject the null hypothesis. So the evidence does not suggest the proportion of 2009 high school graduates in this state who attended college the year after graduation differs from the national value. What potential error could we have made? That's right, a type 2 error. In doing these types of problems, we want to state, plan, do, and conclude. So we want to state what hypotheses do you want to test and at what significance level, and to define any parameters you use. Then, plan. Choose the appropriate inference method and make sure that you check your conditions. The do. If the conditions are met, then you perform the calculations. So you compute the test statistic and find the p-value. Then conclude. Make a conclusion in the context of the problem. And those are the 4 things you should do every single time. Let's take a look at another example. In December of 2009, a countrywide water conservation campaign was conducted in a particular country. In 2010, a random sample of 500 homes was selected and water usage was recorded for each home in the sample. Now suppose that the sample results were that 220 households had reduced water consumption. The county supervisors wanted to know if their data supported the claim that fewer than half the households in the county reduced water consumption. So we'll begin by stating our hypotheses. So our null hypothesis is that P is equal to 0.5, and our alternative hypothesis is that P is less than 0.5. And we'll define P is the proportion of all households in the country with reduced water usage. So we're going to calculate our P hat. So our P hat is going to be 0.44. And we're now ready to move on to our next step. We need to verify our assumptions. So we know that P hat is from a random sample of households. The sample size n is large because our n times P is 250, which is greater than or equal to 10, and our n times 1 minus P is 250, which is greater than or equal to 10. And our third condition, it is reasonable that there are more than 5,000 times 10n households in the country. Now, we'll calculate the test statistic and the p-value. Plugging in our values, we get a z-value of negative 2.68. We'll then look this value up in the table of z-curve areas. Doing so gives us the p-value of 0.0037. We're using an alpha of 0.01. So since our p-value is less than alpha, we reject our null hypothesis. There is convincing evidence that the proportion of households with reduced water usage is less than half. So what potential error could you have made? That's right, a type 1 error. So since our p-value is less than alpha, we reject our null hypothesis. So let's create a confidence interval with this data. So what is the appropriate confidence level to use? Well, since we're testing our alternative hypothesis as P is less than 0.05, alpha would also be in the lower tail. So again, since we're testing that our alternative hypothesis is that P is less than 0.5, alpha would also be in the lower tail. I had to fix that typo. So using our alpha equals 0.01 with our standard curve here we see that we've got our alpha of 0.01 in the left tail, and our confidence intervals are two-tailed. So we need to put 0.01 in the upper tail since the curve is symmetrical. So with 0.01 in each tail, that puts 0.98 in the middle. This is the appropriate confidence interval. So we're going to compute a 98% confidence interval. We'll take our 0.44 plus or minus our 2.326 times the square root of 0.44 times 0.56 divided by 500 and come up with a 0.388 to 0.492. Now notice that the hypothesized value of 0.5 is not in the 98 confidence interval and that we rejected our null hypothesis. So let's go back to the college attendance problem. Remember that since our p-value was greater than alpha, we failed to reject our null hypothesis, and we used an alpha of 0.01. So we're going to compute a confidence interval for this problem. So in this particular case, a two-tailed test, because we're saying that p is not equal to 0.61. And so the alpha gets split evenly into both tails, leaving the 99% in the middle. So calculating that confidence interval is giving us an interval of 0.547 and 0.613. Now notice here that the hypothesized value of 0.5 is in the 99 confidence interval and that we failed to reject our null hypothesis.